มี带上，没有带上。对哦。Testing, testing, testing, one, two, testing, testing. Uh, 妖精，不妖精。Can you help close the door? Yeah, okay, thank you. We will come back from the exam training day. So we won't discuss the exam material because someone haven't took the exam yet. Yeah. By the way, is Zhang Yiyang here? Zhang Yiyang. Zhang Yiyang. Zhang Yiyang. Okay. Welcome back. So, yeah. And maybe if it is possible to release, then I will ask you to get a time, make it an office hour, then you can come to my office and all of you will take turn and see your exam or something like that. Yeah. What else? Yes. And also keep in mind you have a double pass rule, which is all the quizzes, because your quizzes and midterm is 50% and then final is 50%. Both of them have to be like at least out of 100%, 40% of them must pass. So it's like if 50% out of 50% is 20, I guess. So both assessment you need to get at least 20 marks. And then final exam won't include chapter 1 to 3 anymore, but maybe we will just use the language but not tested on chapter 1 and 2 and 2. Okay. So this is the new start. Actually, it's the new start. Okay, we have passed half of the semester. And don't worry. Before we launch into the new chapter, using the one question of this cryptography, which I go through very fast last week. So for this block cipher here, yeah, when you get your key, you apply your key respectively. Okay, so yeah, she asked how to get from 21 to 19. Okay. Okay, to get from 21 to 19, you get 21 and then add 24. Okay, mod 26, you get 19. Which one is easier to see? Everything you need to get mod. So maybe this one is easier to see. So you get 6, okay, you add 24, you get 30, okay. 30 mod 26 is 4. Congruous to 4 mod 26. Okay. So you apply by block and then get a new block, repeat again. Okay. This is for the block cipher. Okay. Yeah. Any question on the block cipher thing? Okay. If no, we'll continue to today's lecture. Okay. I still encourage you to ask questions during the lecture. Okay. Maybe you think that you will like interrupt the lecture, but I will control the flow. Okay. Let me bring up my. Although we can't discuss the midterm exam question, but I still want to talk about something about the way you're answering the question. So I think actually you observe from the quizzes already. If you directly write the answer, you won't have any marks. But if you write out the step and maybe you calculated wrong, maybe you get more marks than directly write down the answer. So your method is more valuable than your answer. Okay. If you can't explain your answer, then no one will believe your answer. So um, no one will believe that they won't access you. So make sure you write out the step explaining your solution. Today we will learn counting. Okay, counting. And then if we finish reading 2 hours, then we'll go to the next chapter, relation. So counting is about counting ways. So as you all know, I was new to this place. So when I first came here, well, I was studying in Australia last time. So in Australia, there's less Asian food, like less economic rice, something like that, which is very common in Asian country. So even they have fewer choices, maybe 8 choices. So every day you will see the same 8 choices. They don't even change it. So we made a we make fun with our other like Asian friends say, there's less choice in Australia to eat. So when I came back here, came to this university, and I went to D6. Okay. So the first thing is I count how many dishes they have. So they have like about 50, including the veg and meats. So 50 of them. So I was wondering how can I finish the three combination of them. So like this is what I told my colleague. Like my colleague, uh, bring me first time go outside. I told him that like inside the canteen we got like if I pick a meal, so like so about 50 dishes, right? If I pick three dishes a meal, for example, 50 times 50 times 50, I actually have how many choices? I think it's like this, like that. Okay. Okay, of course, this combination repeated some of the repeat the dish. But anyway, this is just a rough estimation. So even if I stay in this university for 3 years, I can't finish this combination. So I was making fun with my colleague. Yeah. Okay, so today we will learn how to calculate different ways. Yeah, in speaking about Australia, so actually the rain here, right? You would think that was very strong, very the thunder is very loud. It's like really common. I think it's really common in Malaysia. So even so, when I grew up, like this weather is like, but like I'm get used to this kind of weather. And Australia rain very less. Only when the change of season it will rain. So when it rains, right? I think only the winters. I think wait, the yeah winters and the spring change. The rain will have the smell of the rain smell of Malaysia. Then that time like you will think about home. Yeah, yeah. There's a smell of rain. Next time you can try and smell it. And the smell of the rainforest rain is a different smell. Okay, yeah. So we should start now. Okay, so what did I use to calculate the dishes just now? Actually called the product rule. So what's the product rule? Okay, so let's talk about two ways. So suppose I don't write many things. So suppose that the procedure can be broken down into a sequence of two tasks. Okay. So if there are n1 ways to do the first task, okay, and n2 way to do the second task, okay, then there are product of n1 and 2 ways to do the prediction. Okay. So what example can you get? Mm, so example, yeah. So use back the example. So let's say, mm, there. Okay, so suppose there. Let's make the number small and easy to calculate. Okay. If no. Okay. Okay, if you are allowed to take two, okay, I should say allowed to take one, one, out, three, three, two, okay, one, two, okay. So if you have 3 veg dishes and 5 meat dishes, and you are allowed to take 1 veg and 1 meat dish at once, so how many ways you can get your meal? So you just take 3 times 5, which is okay. Okay. So this is the product rules. So the next one is the sum rule. If a task, so what's the sum rule? So if a task can be done in either way, where you got N1 and N2 ways to do it, okay, where none of them are the same, then there are N1 plus N2 to do it. Okay. So when do we use the sum rule to count? So for example, let's put this example, and then we'll change the question. Okay. So suppose the same question, but now you can only pick one. How many ways? How many ways you can um, if you can only you can only be allowed to pick one fish at once. Okay. So if you can only take one dish at once, you can only take one veg or one meat. So together you got there 3 plus 5. Okay. Is it like blur or clear? So maybe I draw a picture here, maybe it's easier. So maybe you can, for product rules, in this case, you can have V1, V2, and V3. Okay. And then M1, M2, and M3, M4, and M5. Okay. Let's say these are different veg dish and meat dish. So you're allowed to take one veg at one time. So either you get V1, either you get V2, or either you get V3. Okay. And then pair with one meat dish. So either V1 pair with M1, pair with M2, or pair with M3, or pair with M4, pair with M5. Okay. And then you count these pairs. Right. Okay. So these are like the so if you count these pairs, right? Go back to the cardinality of set. Okay. So one set have contain 3 elements, the other set contain 5 elements. And then you compute the product of them. So you need to multiply them together. Make sense? Huh? Make sense? Make sense? Okay. Yeah. Okay. And then for this one, you just either you can pick V1, either you pick V2, either you pick V3, or either you pick M1, either you pick M2. Okay. So altogether you got 8 ways. Okay. Yeah. Oh, this is like repeat the calculation again. Okay, the next one, next one is really what we did in set theory before. So this is the okay. So before that, so not that you should generalize to generalize, generalize to and I use generalize to m ways. Okay, so where m is greater than 2. Yeah. So I only tell you 2 ways, but you can generalize it to m ways. M ways. Also similarly for this one. So you should generalize to m greater than. Okay. So the next one is the inclusion and exclusion for 2 sets. Yeah, this one we really go through already last time. So just recall it. Maybe I don't copy down. Do I need to copy down? Yeah, okay. Maybe I just state it. So I say it differently from last time and then see how are you familiar with this kind of combination. Okay, so if a task can be done in either n1 ways or n2 ways, okay, then the number of ways to do the task is n1 plus n2, okay? But if it is just plus, is the sum rule, right? So we need to minus the number of ways to do that are common two different ways. Okay. So suppose you got one way to do it. Okay. And then you got the other way to do it. Okay. So maybe they have some intersection here, but you only want to count different ways. So you need to take away, to remove this, remove the middle part, you only count the outside. So which means the cardinality of B is actually counting the cardinality of A unit B. Okay, think still remember this one? Okay, so that you don't count the same thing twice. Okay, subtraction rule is for maybe I just put here counting disjoint distinct ways. Okay, counting distinct ways for subtraction. Okay, so few ways to count things. So this one, I'm not sure you heard before or not. In Kaiyosu, it's called the pigeonhole principle. Okay. You see any pigeon in the campus? No? Yeah, I thought there's pigeons here. Cat only? Okay. Maybe get eaten by the cat already. Okay, so pigeonhole. Okay, so what's pigeonhole? Okay. So let's say I have 5 holes. Okay. Maybe this one use picture. I got 5 holes here. 5 holes here. Okay. I have 6 pigeons. How to draw pigeon? Okay. Maybe I just draw like this again. I got 6 pigeons. Okay, I got 6 pigeons here. Okay, I got 6 pigeons here. 6 pigeons to go into 5 holes. There's my at least 1 hole contain 2 pigeons. So if you go here, go here, go here, go here, these two must go. This one must go at least one of them. Okay. So this is the pigeonhole principle. So if you are given a integer, positive integer, and k plus 1 or more objects, place into k box, then there is at least 1 box containing 2 or more objects. Okay. So the idea is easy, but it is quite applicable. Maybe you can look at the literal question later. Okay. So the idea is easy pigeonhole. More pigeon than hole. So one of the hole must contain 1 or more pigeons. Okay. Okay, next. Okay, something more interesting. So next is I think you learned this before, the permutation and the combination. Okay, so what's the permutations? So in permutation, we care about the orders. So even if they are the same choice, but if the order is the different, then we will say it's a different element. Okay. So maybe I give you an example. So I'll give you an example. So for example 1, 2, okay. So this is in the space of R cross R, right? R2 is a permutation of 2, 1. Okay. So you sort first and 2, so commute. So if commute is different, then okay. And so how the numbers of where that we count it is called the R permutation. So and called the okay. So we call it an R. What is R permutation? So an R permutation is an ordered arrangement of elements of a set. Okay. For example, let's see an example. So let's look at the two permutation of the set set or set 1, 1, 2, 3. Okay. So what's two permutation here? So what we have here is we got what do we have? We got 1, 2 here. Okay. We got 2, 1 here. We got 2, 3 here. We got 3, 2 here. We got 1, 3 here. We got 3, 1. Okay. So permutation of 3 set elements. Okay. So how many ways can do it? How do you count actually from here? So first place here, you got 3 choices, right? Okay. And then after you pick one, you only left with 2 choices. So actually the total way is 6. So, that's that. Is what? The number is 3 times 2, which is equal to 6. Okay. Yeah. So following here, we got a theorem. So we can generalize this to a theorem. So if we want to count a general n, then okay, this number we will write as P and R. Okay. I think some more familiar notation for you probably is what is NPR, at least for me. So NPR is PNR. So following your textbook notation is what is m times n minus 1 times n minus 2 n times until r. Okay. This many ways. Okay. So how to prove this? So it's the same as the argument just now, which you use the product rules. Because there are n ways to put into the first place, okay, and then n minus way, n minus 2, all the way out to n minus r plus 1. So I will write here the proof is by sketch using product rules. Okay, where objects are not allowed to repeat. Okay. After you pick the first one, Okay, the first one is gone, you cannot put into the second one. So you're left with n minus 1, then n minus 2, then keep going. Okay. Yeah. If you're confused or any stupid question, you should ask me. Because sometimes you confuse because just stuck at one not important thing. Okay. So what's the corollary? So instead of writing out all these products, right? So actually there's a easier form which you use the factorial. Okay, so what's the factorial? So the formula is n factorial over n minus r factorial. So in case you don't know what the factorial is, so recall. Okay, maybe I continue. Where n factorial equals to n times n minus 1 times n minus 2 times dot 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 up to 1. Okay. So you can imagine if you have n times products until 1 and then divided by n minus r to products 1, then n minus r will start cancelling into 1. So what you left is n up to n minus r plus 1. Okay. You can see on. Maybe I just write it out so that you recall your memory. So n is what n minus 1, n minus 2, n minus r plus 1, r plus 1, and then n minus r times n minus r minus 1, and then keep going. Oh, no space. Let me move it. Right. So this is just indexing. Get used to the index of. Well, if not familiar, maybe it's the indexing. So you should imagine n minus 1 is a number, and then next one is n minus r minus 1, and keep going. Right. So all these term here will cancel. So what you left with is the same product. Okay. Okay. So this one is not too hard. Okay. Next one is the combination. Next one is combination. So what's combination? So combination in permutation we care about order, but in combination we don't care about order. Okay. So maybe 1, 2 is equal to 2, 1 in combination. So for example, if I want to count the number in your class, right, in the number of students in your class, I just need combination. I don't need combination. I don't need to care where you sit, even though you sit different seat every time. I just need to know who are you. Okay. So what's the number of, so how to count the number of R combination? R combination, sorry. So out of n, you want to do the R combination. So yeah. So let's do the example again. So let's do 2, okay, the same example here. 2 com of 1, 2, 3. What do you have? So 2 com of 1, 2, 3. You have, okay. Since we don't care about order, so I might write like this, okay? Because set, remember set, we don't care about order. With set, we only care about disjoint element. So we write this set notation. Just now I wrote like ordered pair notation, okay? So when I write this, typically I'm how to say, I'll say I care about the orders, okay? But set we don't care about orders. So two permutation here, we got 1, 2, 1, 3, and 2, 3. Alright, so there are only three two combination of 1, 2, 3. Okay, so in general, how to count it? So in general, how to count the number? So the number of R combination of a set n elements. Okay. Should I repeat again? So yeah, n have to be in the positive, and R is another integer such that it is in between 0 and n. Okay, equals to C and R, which is n factorial over R factorial times n. Okay, yeah, this one you should be familiar, which is what is this? So remark. So actually, this is the NCR you see before. Okay. So do you wonder how this number come from? Do you ever wonder how this product of numbers come from? Hi. 说说看，我帮你 translate。
可以画圆规三角形，然后地推出来。
You sure? How?
啊
？How?
画圆规三角形。
And then?
地推。
But what's the Pascal triangle have to do with the you say the triangle you talk about is called Pascal triangle as well? Okay, I mean the triangle you talk about. Triangle. Yeah. Oh, okay. No, okay. I mean now I want the combinatory proof. Okay. So how do you count? Count using counting. How to prove this formula here? Okay. So he was saying using the Pascal triangle. I believe Pascal triangle has nothing to do with counting. I'm not sure. I mean, okay, it has something to do with the counting, but it's like counting different thing. So like, okay, never mind. So okay, I got a proof here. So what's this proof? I think this proof is quite straightforward, not to say easy, but straightforward. If you consider the R permutation, okay, so you think about how to count first, okay? If you how to count R permutation, so you first you pick R objects, and then you arrange differently, then you will get different objects, right? So it's exactly CNR times PRR. Okay. So how you do R permutation? So you first take R element from the N elements, okay? Different way of picking them, and then you do permutation within the R. Then you will get this formula. Okay. You believe me or not? You believe me? So let's okay. We also can look at the formula, right? So just now by theorem before. Yeah. If we believe that this equation is true, what we have? This one is n over n minus r, yeah, which is equal to n c n r, which is what we want to find. And then what is this? So this is r factorial over r minus r. Okay. So r minus r is 0 factorial. So 0 factorial is by definition 1. Yeah. So if you move the r factorial across, you will get the CNR. Okay. Yeah. Yeah, we will get to the Pascal triangle just later, which your friend talked about is the called Yang-Hui triangle. Okay. Next. Okay, one obvious property of these CNR is there's a dual property here. So what do I mean by dual property here? So if you replace the R with n minus R, right? Actually, they are the same. So for example, what I mean by that, so I will write out. So CNR is equal to CNN minus R. Okay. This one you can observe from the formula here. Can you observe from the formula here? So if you replace R with n minus R, then this R will become n minus R. And then this will become n minus minus n minus my n minus n minus R. N minus n minus R. Okay. So you get R. So these two terms swap. Okay. So there's some symmetry here. So what symmetry here means? So for example, if you count from here, we will get, if you count like 5, 2, okay, how to count 5, 2 is actually the same as how to count 5, 3. So if you know one of them is enough. Okay, so there's like symmetry here. Okay. So yeah. So for example, if you know 5, 1, then you know how to count 5, 4. Okay. And then 5, 0 will become 5, 1. Okay. Then what else? Okay, nothing. So because I'm like studying the algebra, so I'm very interested in this symmetry here. So if you like arrange them like this, right, in order. Okay. So if you arrange them in order, then this one get rid of it. Then you'll see that they are paired like this. Okay. This is how you pair it out. Okay. Okay. So meaning you need to compute half of it, then the other half is like mirror. Okay, mirror. Okay. Anything else? Okay, nothing else. Okay, so yeah, before talking about the triangle, so another remark 2. One remark again. I think this number also which is called the binomial coefficient. Okay, the binomial coefficient written as like n choose r, okay, is also so CN. Okay. Need to recall what's the binomial coefficient. So let's take example, easy example. For example, you want to expand x plus y to the power square, right? What you get is x squared plus, should I do the full calculation? Okay, I do the full calculation. Xy plus yx plus y squared, which is equal to y squared, plus 2xy plus y squared. So the binomial coefficient is the coefficient of the monomial. So it's 2, 0 here, and then what's this? 2, 1, and then those two. Okay. Actually, I define a remark here is really a remark. So the definition should be, how should I write it? The definition. Okay, maybe your textbook also define like this. Maybe let us put this first. Okay. So in this case, you will see that 2, 1 is equal to 2. 2, 2 is equal to 1. 2, 1 is equal to 1. Okay. It is not accident. Okay. It's not by luck. Because what does this mean here? Okay. So this is like you got this is like how many ways you can pick X, okay, from the product. How many ways you can get X? One X inside your product. How many ways? So there are 2 ways. What are the 2 ways? One way is you get XY. The other way is you get YX. For this one, how many ways you can get X squared? Okay. There's only one way to get X squared, which is X times X. And how many ways you can get Y squared? There's only one way. So 2, 2 is equal to 1. Okay. Yeah, so it's symmetric. So it doesn't matter you want to call this a 2, 2 or you want to call this a 2, 0. Okay, you just need to fix one convention. And why is it binomial? Binomial is because you are multiplying the sum of 2 things. Okay. Okay, 2, 5, 0. We talk about the triangles or we take a break first? Maybe we take a break first and then we come back to the triangle thing. Okay. Let's come back at 5 and then we will talk about triangles. Yeah.
就是你写这个是这样子写的，但是我们在国内是我们必须
这个吗？
对，我们在国内是这样子写的。这样可以写吗？
是 CN 啊，下面是 N， 上面是
R。对，我们是这样子写，可以这样写吗？不对，是很多人都是这样写。
对，
好像我有注意到，所以我就觉得很奇怪，我没有看过这个东西。
我们都是那个
国内的教材都这样，
而且我们写这个也是 ANR。
对，就是这个 PNR， 对，就是 ANR 会等于这个。
OK， 我明白。
这样可以吗？
可以吗？可以不可以？只是一个 convention 嘛。我怕点
写法呀。
对。我知道。
就我们之前也不知道不能这样。
对，当然，我知道，我当然知道。所以，要不我们从现在定一个写法，我们就定这些哦。我怕等下我一看乱去，但是如果考试如果你用了那就算了，我就会知道，那我就。难怪我就看到有些怪怪的符号，然后就没有看过这东西。然后我觉得是反的，但是是反的。
都写反了。
对啊，我就觉得很奇怪。可以啊。
就是这个02是什么意思？
它那个跟那个是一样的，就是那个 CNR 是一样的，就它有3种可能方式，就是没有我们学的那种。
这个没听懂。
这个就是 C20啊
，202等于1。
对啊。
对。
这个是 C20，这个是 C21。
然后我刚才是解释 这个不是一个意外，这个的意思是说我们怎么
这个不是
选，
像是定理吗？
就我们怎么选 x square，有几个方法选 x square，然后这个是什么？有几个方法来选它的 product 里面有一个 x，然后这个是怎么选y square 这样。
嗯。
OK。嗯。诶。
这个东西可以用，这个跟这个是一个意思。
什么东西？
这个
刚才你同学告诉我，等下我告诉你。
好的。
你同学有告诉我。
那你那个题可以。
对，这样就没办法就用了，这至少我知道，因为我有看到，所以我觉得很奇怪。对，幸好你没有告诉我。我看到答案是对的，然后我看到东西是反的，我就想很奇怪。你们早上有课吗？没有课，今天就这一节吗？10点到2点。
对。
奥金啊，your name, how to pronounce your name? 奥金啊，OK. Cause I first three is like 捕妖精。 Close. Okay. Outing. Okay. So class got two house, 堂号 and 同号. 同号, 陈号, 区号. Okay. 同号 huh? You know 同号? Who is 同号 ah? Oh, 同号 there. Okay, okay. Because I see him taking your paper last. 堂号, 陈号 and 单号, 单号. Okay. Okay, let's start. And then list you can sign. Okay, so what's this? Yeah, before that, I have to address another question. So I heard that you're from China background. You got another notation, right? So for now, we got this one, we got this one, we got this one. Okay. So you said that you have like this. Is it? Did I have that? Okay. If you use in the exam already, then I will take note. Okay. If not, maybe we fix like this first. Okay. We fix this three way to write it. Okay. So we standardize in our exam here. So maybe we use these three. Okay. So this one I will reserve. I will check in the exam. I did observe some of you write this, so I was like thinking why you invert the n and n. Yeah. Okay. So we standardize, we use these three, okay? So this one, that's like, okay? We standardize the notation, we use this three. In case I confuse myself. Okay. Why is it this Pascal triangle here? What's this Pascal triangle here? So there's one theorem here, which is called the Pascal identity. Okay, so let's see what's this. Hey, so when you learn the Yang Hui triangle, did you learn about Pascal? No, huh? Okay, okay, this is really different than me because I only know Yang Hui like 2 years or last year, 2 years ago or last year. Okay, let me tell the story later. So, okay, we want to actually this triangle is coming from this identity. So if you want to get the next n plus 1k, you need to take the previous n and then take the adjacent k. Okay. So for example, what's this triangle here? So this triangle here is like, okay, 0, 0, you start with 0, 0, okay. So how to get 1, 0? So how to get 1, 0 is, also don't have previous case, right? So you need to start with these three guys first. Okay, start with these three guys. I think these guys are easy to compute because you have 0 thing to pick from, right? Hey, did I put the wrong thing? No, right? Okay. So you got 0. This one is by definition 1. Okay. This one you cannot count by definition 1. So you got one thing you don't need to pick. So there's only one way, right? Empty set. And then you got one thing to pick one. Then that's the only thing you can pick. So it's 1. Right? Okay. And then the next one, I think next one should work. So 2, 1. So how to get 2, 1? So 2, 1 from this formula tells you that you take the previous n, okay? 2 previous 2 is 1, okay? And then you add up the previous k minus 1 and k. So k minus 1 is 0, k is 1. So it's exactly these two. Add up together, you get 2. Okay, which mesh up what we count just now. And then 2. Okay, 2, 2, 2, 2. Okay. Okay. And then what else? Yeah, and then you can keep going. The Pascal triangle thing. Okay, so you can go like this and go like this. Then keep going. Okay. So what you have is, okay, I write down in this triangle here. So it's 1, 2, 1, and then 1, 3, 3, 1, 1, 4, 6, 4, 1. And then you can keep going. So it's really convenient to build this triangle here because you just put 1 at the outermost and then you just add up the 2 adjacent to get the middle one, and then you get like 5, 10, 10, 5, 1. 2, 5, 1. Okay, so you can see that the duality here. So the opposite one is the same. Okay, this one is the same. 4, 6, and then 1, 3, 3, 1. Okay, so you can see the pattern here. So it's actually called the Pascal triangle or the yeah. Yeah. Yeah, so I put this Yang Hui triangle on my website. Yeah, this is the Yang Hui triangle. Is it? Yeah, I found it from the other place. Then I look for wiki. Oh, I actually got it. Because we never talk about this Yang Hui triangle. Yeah. Okay, and one, oh, I cannot draw. So can I draw? So 1, 1, 2, 3, and then 1, 3, 5. 1, 3. Yeah. 1, 3, 6. Okay. Huh? What? What? Yeah. Yeah. So different civilization have looked at the same thing. Cool. So why is this true? So actually, why is this true? You can just do the algebraic manipulation. So you just write out the formula and then try to add them up. Okay. So for example, yeah, use algebraic manipulation. Okay. I'll use the factorial formula. I think it's a good exercise for you to do. Okay. Use the factorial formula and then verify it. This one can quickly help you compute the binomial expansion. Okay, we will do it in the tutorial exercise, I think. Okay, binomial expansion, then you don't need to expand everything to find the coefficient. This is the way to find it. Okay, let me give you an example then. So for example, if you want to do this, okay, x plus y to the power 6, to the power 6, okay, and then maybe I ask what is the coefficient? You know coefficient, right? The number that multiply in front of the monomial. So what is the coefficient for example, x to the power 3y squared in here? Okay. So you don't need to go back and expand x plus y to the power 6. Okay. You just need to find 6, 3. Okay. 6, 3 or 6, 2. Either of them should work. Okay. Where 6, 3. Okay. Sorry. This is not the monomial. Yes, this is the monomial. Okay. So the coefficient of y cube, s cube y cube is exactly 6, 3. Okay. Depend on you. If your formula is quick and then you go and do this, or maybe you draw the triangle is faster, so you draw this triangle here. Okay. So what is 6, 3? 1, 6, 15, 20, 15, 6, 1. So 6, 3 is 20. Which is okay. So 6, 3 is yeah. Yeah, you can use the triangle or you can use the formula. But don't try to like expand this term here. You can use the R combination. Okay. Any question or not? On permutation, combination, product rule, sum rule, and what? Subtraction rule. If not, then we are done with this topic. We are done with this topic. A bit boring. Okay. Any question? If not, then we are done with the use 1 hour plus to finish one topic. The next one will be more interesting, this one, relation. Okay, actually you realize, right, some of the topic is different with the chapter number in the course, in the textbook. You should follow our numbering, okay? Search for the right chapter. So the next chapter, next topic is relations, okay? So this is in the chapter 9 in the textbook. Okay, relation is, I think it's more interesting. So let's talk about relations and their properties. Okay. So every time, like last time, I talked to you that what's the relation between two sets? What's the relation between two propositions? Okay. So we are always look for relation. Okay, look for relations. So what are relations? So let's take two sets. Okay, we have two sets, N and B. So we want to form a relation called binary relation. Okay, binary because there are two of them, so binary. So what's the binary relation from A to B? Okay, it's another set. Yeah, it's a set. It's a subset. Subset of what? The Cartesian product of A and B. Okay. So when I give you a relation, then you need to tell me which two of them is together, which two of them is together. Okay, it's a subset. So yeah. So actually, in other words, a binary relation from A to B is a set, let's call it R, of ordered pairs. Okay. So that's what does ordered pairs mean? So the order is important. Like A and B, B and A. So they are representing different things. So typically we will write A, R, B, okay, to say that the ordered pairs AB is in the set because binary relation is a set. Okay. If they are not related, we will say A cross B to denote. AB is not in the set. Okay. So what kind of relation you have seen already? Can you give some example? What kind of relation you have seen? For example, functions, right? Functions, graph. Okay, graph. Graph, for example, x, fx. Okay, these are ordered pairs. Okay. Depend on your domain. Okay, ordered pairs. So these are functions. So functions is one of the relation. Actually, congruences. Okay, you just finished the exam, right? Congruences are also relation. Okay. Okay. For example what? For example, in in mod mod 5, okay, in mod 5, what are the same? So 0 and 5 are the same, okay? And 0 and 10 is the same. 0 and 15 is the same, okay? How about 1 and 6 is the same? 1 and 11 is the same, and so on. You can list a lot, okay? So if they are congruous to each other, then they are in the same relation. Everyone following with this example here? Okay. Okay, next. So, any question? Any question on this congruence as a relation? No. Actually, divisibility. You also learn, right? Divisibility are also relation. For example, if A divide B, then we will say that AB is in the relation. Okay. For example, what? For example, 2, 4, 4, 8, 3, 9, 4, 16. Okay. They are all in the relation. If A can divide B. Okay. For example. Okay. So it's like pairs, then you need to tell me how they are related. Okay. They are related by a function. Okay. If I add f to x, I will get this number. And then this one is what? In mod 5, meaning these two congruent to each other. So if I take the difference, it's divisible by 5. This one, if A divides B. So everything here will be A divides B, A divides B, all the number. Okay, all the pairs here. Okay, I think so far is what we've learned. Okay, next, we need to look at some property of the relations. Okay, so for example, a relation on a set A. Okay, but not that binary relation. We want two set, right? So actually, what is a relation of set A? It is actually a relation from A to A. So when you take A and B is the same itself. Okay, A to A. Okay. So for example, so for example, like if for the function, if I pick x is in R and then fx is in R greater than 0, then these are different sets. Okay. But in congruence, we are looking at binary relation from maybe different color. Relation from Z to Z. Both of them are from Z. Okay. Divisibility also from Z to Z. Usually, okay, usually. Yeah. Yeah. I think I only define disability for Z, right? But some of you write decimal, so maybe I just let it pass this time in the exam. Because when I got a question about divisibility, then you guys talk about decimal or fraction. I think I'll just let it pass this time. But next time you need to take note where my definition defined. Okay. I think I only define this divisibility on the Z. Okay. Not on real numbers. Anyway. Okay. So what kind of property a relation can have? So we can say that a relation, there are three properties we are interested in. So one is reflexive. Reflexive. So what is reflexive? Reflect, you know, right? Reflect. So reflexive. So you reflect to yourself. So that means your relation must have like AA is in R as well. Okay. So AA is in R. So AA is in R for OA. Okay. So maybe we can look at the example again. If I say that AA must be in A for OA, okay, what graph can satisfy this? What graph? What graph can satisfy the reflexive property? What graph? Can you answer? This kind of question is the question I like to put in the quiz or exam, right? If you can answer, then this will become the quiz question. Can you answer? Can you answer? Do you recognize this kind of question is the question that I like to ask? What graph can satisfy the reflexive property? I give you 2 minutes. If you can solve in 2 minutes, then solve it. Okay, I give you 2 minutes to think. You can discuss among each other. Not graph. What graph can satisfy the reflexive property? What graph? Huh? X. What is X? Oh, yeah. So usually we don't talk about y equals to x anymore because we know the idea of function, right? Actually, we will write fx now. And fx equal to x. Yeah, right? Because you want this property to be true for all a, right? Okay. You want this property to true for all a, so you want meaning this one is equal to a, okay, for all a. You want to be true, you want this to be true for all a. Things fa has to be true, has to be equal to a for all a, then fa has to be equal to a for all a, then which is f is equal to x, the identity function. Hence, f has to be the identity function. Okay, good, very good. All right, and you also can see that actually congruence also have this property. Congruence is reflexive, right? Because a is mod a is congruent to a mod n. Okay. Okay, how about divisibility? Divisibility is also reflexive, right? Any number divide itself because a divide a. Okay, go away. Go away. Okay, my set is the. Okay, so they are all reflexive in this case. Maybe some are not. Okay, next one. And I can go a bit slower because we're quite fast. We really need to we really need to like absorb these three properties here. Okay, so first is reflexive. The second one is symmetry. We really need to absorb these three concepts here. So another relation is symmetric. Okay, what does it mean by symmetric? It's like if you cut yourself into half, do you think you are symmetric? Left to the right. Okay, maybe not fully symmetric. Okay, there's some symmetry then. Okay. Okay. Or you cut the triangle, cut the same side triangle, and you cut into half. There's a symmetry on the left and right. Or you cut the car into half, the car is symmetry on the left and right. So symmetry here means if BA is in the relation, then AB is also in the relation. Okay. So if AB in the relation, BA have to be in the relation, whichever side. Okay. Both of them have to be in the relation. Then either one of them is in the relation. If you got symmetry, there's another property called asymmetric. So asymmetric is something we'll look after this part here. So maybe we introduce first. This is not as important for now. So what is anti-symmetric? So if AB, BA both exist, again, both in the relation, If AB and BA both in the relation, then A must be equal to B. Okay, previously we don't need A equal to B, but anti-symmetry you need. It's called anti-symmetry. And okay, let's look at the example then. So which example? Maybe 2. Okay, use 2. So congruence. Congruence is symmetry or anti-symmetry? Guess one. Congruence is symmetry. Okay. Because if A congruence to B mod M, then B is congruent to A mod M. Yeah. They are just different by a minus sign, right? Yeah. A minus B divided by M and B minus A divided by M. Okay. But divisibility is what? I already used but already. Is symmetry or anti-symmetry? Your guess is anti-symmetry. Okay. Because if you imagine like 2 divides 4, does it imply 4 divides 2? No, right? So actually you can prove that this is wrong. So actually you can prove that if A divides B and B divides A, then B has to be equal to A. Okay. Only yourself can divide. Because if A divides B, then B is greater than A, then yeah, then you argue why they have to be equal. Okay. The third one is transitive. Okay. So now you talk about first is reflexive. You talk about yourself. You and you is in the relation. Okay. Second, you and a different guy, both of you are in the relation. So if I change the order, you're still in the relation. The third one is three of you together. So it's called transitive. So what does it mean? So we want to look at 3 of them. So relation on the set A is called transitive. Okay, transitive. So transitive is like transit. Okay, go to the next one. If AB, if whenever AB is in R, BC is in R, then A and C is in R. Okay, for A, B, C, and B. Okay. Okay. So if I'm good with you, and then if you are good with him, then I'm good with him. But this is not true in the relationship. So when this is true, we call it a transitive. So for example, congruence again. Congruence is transitive. I think congruence is transitive, right? Did we prove this? So the statement is if A congruent to B mod N and B is congruent to C mod N, is it true that A is congruent to C mod N? Did we prove this or not? No. I think it's true. You can try and prove. Okay. Divisibility is divisibility transitive. I think yes, it's transitive. think we proved this, right? If A divide B, I think we proved this, A divide B and B divide C, then A divide C. I think we did this proof before. Yeah, this one proven last time. Okay. Yeah. So you want to know whether yourself is inside the relation or not? You want to know you and the other guy is in the relation or not, if you change the order. And then you want to know three of you. If you I know about A and B, I know about B and C. Is there any relation between A and C? If there is, then it is transitive. Okay? Yes. So now we can define this thing here. The last time you were confused about what I talking about the last time. I'll give the example back again. So now we will introduce this thing called equivalence relation. Equivalence relations. Okay. So first of all, equivalence relation is a relation. Okay. Remember the binary relation? The relation is a set. Okay. Between an ordered pair. Relation between an ordered pair. So this relation, when we call it an equivalence relation, only when the relation is have three properties. First is reflexive. Second, symmetric. Third, transitive. Okay. Only these three properties together, we call the relation equivalence relation. Okay. And then, yeah. Okay, I want to quickly jump into the example first, then later we can introduce other terminology. So just now we proved that the congruence are or is reflexive, symmetric. Okay, so reflexive, A mod A is congruent to A mod A. Symmetric, I can swap A congruence B, B also congruent to A, and transitive. Okay, so hence congruence is an equivalent relation. Okay. So what's good about this equivalent relation? So we can talk about two elements are equivalent. Okay, not equal but equivalent. They are not equal on the spot, but they are equal on the nodes. Okay, they will say on the nodes. They are not equal on the nodes, but they are related. They are equivalent. Okay, they are not equal, but they are equivalent. Or equivalent. Okay, so we won't put equal sign there. Okay, normally sometimes we will put the curly line, so like this curly. Okay, so curly. So for example, let's go to the congruence. Which mod you want? Pick an integer. Pick an integer. What's your favorite integer? Positive one. Quick. Pick one. 2, 8. Okay, can 8. Good. So 8. Okay, mod 8. Which two are equivalent? So for example, 0 and 8, no? 8 and 16. 16, 32. So you can jump further, 16 jump to 64 again. Right? By transitivity or anything. Or definition also can. Also, 1 is related to 9. 9 is related to what? 17. Okay. 17 is related to 32. Okay. Yeah. So actually, we will group these guys together. Group the equivalent elements together, which we call the equivalent class. So definition. So let's group these. Since they are all the same, right? We can put them under the same roof. Okay. So the set of all elements that are related to an element A of A is called the equivalent class. So under this class, they are the same. All the elements under this class are the same. What do I mean by the same? Is equivalent. Not the same on the nodes, but they are equivalent. And we will write denoted by your textbook. I think write this, but my notation is this. Okay, both of this accepted. So for example, just now we go back to the equivalent class. So the congruence mod 8, right? Congruence mod 8. What is congruence mod 8? Actually, Z8. Okay. So under the equivalent class of 0, what do you have? 0 bar. You have like -8, 0, 8, 16, 32, 30, 31, 40, so on. Okay, because these are equivalent to each other. Mod 8, 1, you have what? You have like -1, 0, 1, 9, 17, 25, so on, right? And then 2, you got what? You got -2, 0, 2, 10, 18, 26. Okay. So similarly, you can write equivalent class for 3, 4, 5, 6, 7, and 7. 8 is the same equivalent class 8 as 0. Okay. Remember last time I think I talked about this, saying that the 0 up to 7 can think of them as a set. So why I can think them as a set? Because they are equivalent to each other. You yourself is equivalent to yourself, and then every two numbers are equivalent to each other. And then if you have equivalence between two of you, then the first and the third one is equivalent. So I can put them under set. Okay. So this is the equivalent class. So instead of thinking of number 0, 1, 2, 3, 4, 5, 6, 7, up to 7, you can think of each of them as a set. And inside the set, all the elements are equivalent to each other using the relation mode, using the relation. Depend on your relation. Okay. Is it clear? Is it clear? Right. So any two you pick, there should be relation between them. Okay. Okay. So this is the word I mean. So you got different word in modulo. You got different word, different set. Okay. So for example, what's the equivalent class of 10 in this case? What's the equivalent class of 10? What's the equivalent class of 10? Yeah. So equivalent class. So the equivalent class of 10 is equal to the set of the equivalent class of 2. Okay. So they are equal by the equality of set. Okay. That's why I put equal here. This equal, wait. This equal here mean equality of set. Okay. That means you need to show the subset in thingy. You need to show the subset. Okay. Okay. Next. So maybe I jump into here first. So next we want to see that actually the equivalent classes will form a partition. Okay, I want you to observe one thing inside this. Observe first. If we can observe, we don't get into theory, then we could take a break from here. So let us observe here. Okay. So congruence is a relation in Z, right? So congruence is a okay, let me write here relation on Z. Okay. You can see that if you pick any number in Z, okay, it lie in one of the set here. Okay. Maybe you give me one integer. Give me one integer that you like. Give me one integer. Hey, why I put 0 here? No one told me. Give me one integer. Hello? Give me one integer. Give me one integer. Sharp one. Huh? Give one integer. Oh, you cannot give integer, man. Give one integer. Hey, quick. Cannot finish class like this. Give me one integer. Give me one integer. Quick. One integer. Any integer. Give me one. Huh? Quick. Hey, no rest if you cannot shout out one integer. Quick. One integer. Wait, so high. 0. No, 0 already. I told you where is it, right? So 0. So let me put. So 0, you take one integer here. I can show you every integer is in either one of the set. For example, it's 0, 0 already in here. Okay. Another one. Wait, another one. Pick one more. 1, 2, 3, 4. 3. Okay, I will show you where is 3. So 3 is here. Okay. Maybe pick a large one. 1000. Okay. Because I asked one, so you have to tell me where is 1000. Huh? -1? Which equivalent class? 0 up to 7. Which one? 1? You sure? So 8 is what? 8 is 8. 20. So 8, 28, 2, 16, 40. Aye, 0. 0, right? So 800 is here. Right? Again? Hey, sorry. 1000 is here. Okay. So that's mean what I'm trying to say is given every integer here, okay, I can show you it is either in one of the equivalent class, which means this, if you imagine you got a set Z, okay, actually it's infinite, but I cut it infinitely as well. So you can imagine a set, then I cut it. Okay, I cut it into how many pieces? 1, 2, 3, 4, 7. Okay. I just customize myself. Okay, so I cut it into 3 pieces here. So every number in the Z is what? Is in either this 7 region. Okay, if you think that it is infinite, right? So if it is infinite, then I remove the boundary. So maybe I remove the boundary like this. So I remove the boundary. And maybe I don't need to do this first. So I remove the boundary. Okay. So imagine keep going on, keep extending. So keep extending. So you can keep extending, remove the boundary, So we got like this. That's infinite. Remove the boundary. Okay. I got infinite here. Okay. Imagine this plan like get bigger and bigger. Okay. And this is only can doable with iPad. Okay, and then I split into 8. So one of the any number will be any element will be grouped into one unique equivalence class. And then we will see why next week. Okay, so every equivalent class will partition your set. I just show you one example here. And we will see why in general it is true. So partition of a set is the same as equivalence relation. We will see why it is true all the time next week. I'll only show you one example for mod 8. Mod 4, mod 6 also can. That's why last week, 2 weeks ago, I write one confusing notation. I'm not sure how many of you remember. So I wrote something like this. Then I never wrote in the other 2 class already. I get them confused again. I wrote this notation, if you remember, from 2 weeks ago. I put the raw lecture notes online as well. It's inside the midterm revision. So midterm revision file actually got all the recordings and also raw lecture notes. Meaning every time what I draw here, I put it there. The one that I upload every week is like I already edited. So why I write like this? So that means I take the Z, okay? I take the Z, I mod out by this 8Z relation. Okay. So that's why I put this notation. So you can imagine the whole Z, the infinite Z, and then mod out by the 8Z relation. So you become 8 parts. Okay. So this is why I wrote this notation here. For this notation, what you learn is only just like 8 number, right? So this is a finite set 1 up to. Okay. So the equality here is actually it's an isomorphism. So it's okay if you don't know, but the idea what I want to say is on the picture. Okay. So I mean, what I want you to appreciate is about this notation here. So I got Z, got all the Z, and then I'm brought out by this 8Z relation. So I have 8 groups here. Okay. And then this notation just says there's like 0 up to 7 because Okay. Any question or not? Yeah. It's okay you don't know about this part, but I want you to appreciate the difference of 2 notation here. Okay. If you want to know about this part, please take mathematics. Algebra. Okay. Otherwise, Okay. Any question? No? Okay, very good. Finally got someone answer me. Okay. Very good. Good improvement. So we will take a break until 6:03 and then we'll come back for tutorial questions. This week should be quite relaxing, I guess. Yeah.
那这个C 上面都把它表示出来。
这个这一个是你之前学过，对你这个里面的意思是说你里面有0到m减1， 所以这一个情况是8减1，所以是7，所以里面有0到7个数字。
如果这个下标是一个，比如说大于0的话，
对，
就是一个大于0的整数。
对，一定要一个大于0的，对，一定要一个大于0，对对对。
这边这块是什么？
对，这一边的一块就是我今天想要解释的这个 partition 的概念，就是我把整个 Z，OK， 我有整个 Z 啊，假设这个是一个无边无际的东西，然后我要把我的 element 全部用8Z 的 relation 把它拆分，比如说刚才我说0和8是一起的，因为它们的分别是倍数，8的倍数，所以这边有8咯，这边也是一样咯，这边的这边的什么呢？这边的actually 我有错，你们没有提醒我。
是，
这里应该不是减2，这里应该是减7的。
对。
然后这里应该是减6。OK。Anyway，but 我想讲的就是OK， 我想讲的是每一个这里的数字 ，OK，我把它拆分成8个区域，怎么拆呢？只要它们之间是8，它们的差别是倍数8，比如说0跟1的分别是倍数8，不是吗？
不是，
所以它们不活在同一个区域，但是0和8的分别是倍数8，所以它们就活在同一个区域。那以此类推，你就可以把它全部
就可以分出8个区了。
对，
所以那个符号就是这个意思。
对，
那个等于号呢？
哪一个？这个等于号啊？这等于号，这个等于号啊，这等于号的意思是，目前没有意思。对，
那
要有意思的话，要介绍新的概念。对，但是我想让你们知道，
它跟我们之前那个等于号不是一个意思。
不一样，也不是 set 的等于，因为你看这边这么多东西，这边只有一个东西吧，所以不一样，这个等于号不一样，所以讲不出现在，因为没有概念。所以就我就要你知道是两个，在某个程度上面他们是相等的。
明白。谢谢老师。
我要问这个 R6是 transitive 是吗？是看
因为它只有一个东西在里面吧，
是一个东西就可以是 transitive，
因为你要比较3个东西嘛，但是你现在只有2个东西，所以你就一个东西，对，
所以只有一个东西就可以这样讲，
就没有3个东西让你比较，所以就 vacuously true， 还是那个 vacuously true。
对，
像 empty set 如果你没有东西，你就是没有东西让你比较，所以那个 statement 是 OK， 我们再回来 proposition 了。你看它这个是什么 ？if 这个 and 这个if 这个 and 这个 then 这个嘛，对不对？但是你这边是 false 的嘛 ？if false then 全部 imply 就对了。proposition。
Thank you.
Okay.
Yeah. Just now, can I slide right?
Yeah, you slide.
What? This one? How? Just now, what's the method to find that 1,000 belongs to zero part? I don't really understand the method.
Okay. First, do you know what this set is?
Mm-hmm.
I'm asking. So what this set is? Do you know?
From 0 to 8 and then times 8, right? But
so there are multiple, so their difference is multiple of 8. Okay, so one thing you need to check is whether this guy is the difference between all these guys with 1,000 is a multiple of 8 or not. Or in other words, is this congruent to 0 mod 8?
Just to decide like that.
Yeah.
But what if I chose a number, but then I divided that decimal? What if?
What do you mean?
For example, I pick a random number.
You pick a random.
69.
69. Okay. So which equivalent has there?
Yeah. How do How do you decide that?
So what is 69? What is 69 mod 8? What is 69 mod 8?
Set by mod.
Yeah. What is 69 mod 8? It's congruent to
Big times take 60.
5, right?
Mm.
5 mod 8. Yeah.
Does
So
that
that means it live in here, 69. Okay.
set by mod.
Yeah, the 7 mod. Because my relation is not 8. Okay.
Thank you.
Okay. Yeah. Yep.
Reflective.
Reflexive. Yeah, what do you want to talk about?
Is it always true as long as what?
What do you mean? But if it
What
is
does it say?
whether okay, relation between two things, right? So this reflexes mean if the two elements are the same, does it still satisfy the relation? If you give a relation, okay, because relation have to talk about two things, right? But when these two things are equal, does it still satisfying the relation?
Oh, so it's like, for example,
For example,
a square then it does not satisfy because it is not equal.
wait, say again.
For the graph of like
Oh, okay, yeah, okay,
then
yeah.
it's not
So you mean like x squared, huh? Yeah. Okay. Only one point is reflexive. Okay. Okay. Yeah. But okay. Yeah. This one. Okay. But this reflexive have to be true for all A. So there's no one point. But I mean, yeah. If you pick, two, then 2, 4. Yeah. 2 is not in the set. Yeah.
How is this different from this? I guess
Oh, this one is just says that if AB satisfy the relation, BA have to satisfy. But the next one is if both of these are in the relation, then A have to be B.
or else it's inverse.
No. Anti-symmetric means A have to be equal to B if these two exist. If these two are true. But this one doesn't require A equal to B. Can you see it?
Two equals to 4.
What do you mean? No.
Then it's anti-symmetric. Well,
No. 4 doesn't divide 2.
oh, so wait,
I was trying to say that this is not symmetric. This one is not symmetric. Not symmetric.
so it's anti-symmetric, right?
Not symmetric, but anti-symmetric. This line is just this line is just telling you it is not symmetric.
Not symmetric and asymmetric.
It's different. I think it's different concept. Different concept.
Not symmetric.
It's not negation of each other.
Wait, so not symmetric.
You can be not symmetric and not anti-symmetric.
Oh, okay.
Yeah. It's not negation. It's a different concept.
Oh, okay.
Yeah.
But this is anti-symmetric. So like this one is 2 is A and 4 is B, right?
And then
so does this?
what do you
Wait.
mean?
Then
it doesn't satisfy this.
yeah, it doesn't satisfy.
4-2 is not in the relation.
Because this one.
Because of this line here. You need to prove this. I think. Oh yeah, this is not proven. You need to prove this.
But then if this one is proven, then
Yes.
so this one does satisfy the anti-symmetric thing, but haven't proved it.
Haven't proved it yet, but it's true.
Okay.
Yeah. Yes. Yeah. Okay. Yeah, just now one of your classmates touched on a good concept here. good. So symmetry and anti-symmetry are not negation of each other. So it doesn't mean that if it is not symmetric, then it is anti-symmetric. You can be not symmetric and not anti-symmetric. Okay. So these are not something that implies each other. Okay. In particular, this line here, I'm just saying that divisibility is not symmetric. Okay. And then this line will show that divisibility is anti-symmetric. Okay. If this is not true, then it is not anti-symmetric. Okay. Yeah, just now there's typo here. It's not -1, -2 here. They are not congruent to 2 or 1. Okay. And then this equal sign here is not set equality. So this is something else. But what I want you to know is they are equal at some level. Okay. Some level they are set the same in some level. Okay. Okay. So you can any question or not? Any other question on the lecture? Yeah. I didn't go into technical stuff, but I want you to observe some phenomenon here. Okay. If not, we can jump into the tutorial question for today. 这个不要。或者有点危险，如果被处境就或者说，我知道你要表达什么，但是不是这样表达，就算你这样表达，我觉得一个危险的地方就是把被冲击了。也不一定有时候在那里想被冲击，就开放式的。但是应该这个处理，我觉得这个处理而已。类似的不是就是也就把你因为那个确认说你要添加。但是主要的是你要知道有一个重点就是你要帮助有点，然后你只要保证风险就不管你要怎么表达，但是重点是你要接到那个点，然后去要保证 You want to discuss now, or you need more time? Huh? You want to discuss now, or you need more time? Do you want to discuss now, or you need more time? More time? Okay, maybe we have another 5 more minutes, and we'll discuss. Huh?这是我选的吗？不是哎，这不是我选的是吧？我有选这题吗？你那题是哪一题？6.1啊？这个我有选了。哎，我没做。嗯，对啊，对啊，对啊。 Hello. Okay. Let's do some discussion before we dismiss. 6.2.1. 6.1.2. So show that if there are 30 students in the class, then at least is it this one? Oh, not this one, right? Let me go back. 6.1.2. An office building contains 27 floors and 37 offices on each floor. How many offices are in the building? So you should imagine one floor, you have 37 offices. So you got 27 floors, then you use product rules. Okay. 6.1.26. How many strings of 4 decimal digits A do not contain the same digit twice? So meaning you got 4 decimal digits, but after you use up one digit, you cannot repeat using it. So you got 10, 9, and 7. So this is the 4 permutation of 10 elements, 10 digits. Okay? 4 permutation of 10 digits. And what is this again? Next one is end with an even digit again. So others, you got all the choices. So the first 3 place, okay, let me draw them. So first 3 place, you got random. Okay, you got 10 choice, 10 choice, 10 choice, but only got 5 choice here. Okay. And then this one, after you use up, cannot use the same. Yeah, this is also 10 P4. Okay, this number. And then what? C. C is have exactly 2 digits. Oh, this one. Okay, has have exactly 3 digits that are 9. Okay. So is what? So first you need to have like 999 something, or 99 something 9, or 9 something 99, or something 999. Okay. But this one cannot be 9, so only left 9 choice. So you got 4 times 9 choice. Okay. 6.1.28. How many license plates can be made using either 3 digits followed by 3 upper English letters or 3 upper English letters followed by 3 digits? So 3 digits, no restriction. With 3 upper English letters or mod 26. Okay. Remember from the crypto. And then 3 upper case English with 3 digits. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then add them together. Product rule with sum rule. So the whole thing is a sum rule. Single is a product rule. Okay. Stop me if you don't understand. Stop me. I'll just go through first. Stop me if you don't understand. How many big string of length 7 either begin with 2, 0 with 3, 1, 6? So remember the big strings bit only got 0 bit and 1 bit. So your string is length 7 now. And then the condition is either 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Either you start with 2, 0 or you end with 1, 3. Okay? So how many possibility here? So 2, 2, 2, 2, 2, 2, 2. Hey, did I draw too many? 1, 2, 3, 4, 5, 6, 7. Okay, too many. This one? 1, 2, 3, 4, 5, 6, 7. Okay. So here got 5, 5 waves. Okay. And then here got 4 waves. Okay. But remember that you can have 0, 0, also have 1, 1, 1 together. And then 1, 1, 1 with 0, 0. So actually you already counted the possibility. So you need to take away the 2 possibilities here. So take away the possibilities here. Okay. Take away one of them is enough. Understand or not? Let me draw in the rings. Let's say you got piece. So you need to take away this kind of, because you are counted. If you counted separately, you will count this case. Okay. That's why you use the inclusion exclusion. Okay, 6.2.2, you want to use the pigeonhole. Okay, your classmate asked me how to say that you use the pigeonhole, right? So the important thing is you need to tell me what's the number of the holes and then what's the number of the pigeon. Then you can use the pigeonhole principle. So the K here is what? Let me see what's the question. So that if the D and at least, okay. So the question here show that if there are 30 students in the classroom, then at least 2 have last name begins with the same letter. Because the letters only mod 26, right? There's only 26 of them. So if you have, so this is the holes, okay? And then the number of pigeon is 30. So there must be, by the pigeonhole principle, then they must repeat the last name with the same letters. Okay. So you need to make sure your pigeon is at least K plus 1, okay? At least K plus 1. At least, okay. So the problem is if you have K of make sure you have at least, meaning you can K plus 2, K plus 3, at least K plus 1, you can K plus 2, K plus 3, K plus n pigeon. Okay. Pigeon to apply the pigeonhole principle. Okay. Okay, next 6 to 6. You got 6 professor and then you got 0 to 100 marks. And then you want to find how many students so that you have 2 students from the same professor who earn the same final exam score. So you got 0 up to 100. So how many numbers here? How many numbers? 0, 1, 2 up to 100. There are 101 score. And then you got 6 professor, right? So let's say the worst case, right? Worst scenario is like all 6 professor, P1, P2, P3. I change professor into symbol. P1, P2, P3 out of P6, and then every one of them got 0, 101 student with different marks, right? So by pigeonhole principle, you just need to make sure you got 6 times 101 plus 1 at least. Okay. So you just need to make sure you got at least 607 students. Then you can use pigeonhole principle. 6.2.20, what is it? Suppose that there are 9 students in a discrete math class at a small college, so that the class must have at least 4 male students or at least 5 female students. So how to show this? How can you know from here? So you can just use the contradiction. Suppose there's more than at least, okay, so suppose there's less than, negate, less than 5 male and less than 5 female. So less than meaning 4 or less. Okay. 4 plus 4 is 8, but your student have 9. The total number is 9. So it doesn't match up. The next one is at least 3 male and at least 7 female. Okay. Similarly, you use a contradiction. Suppose there are less than 3 male and less than 7 female, which is 2 plus 6. 2 plus 6 is also 8. So contradict that you got 9 students. Okay. I think this result is quite strong because from here you can estimate how many males and female. Okay. Yeah, although you don't know the actual number, but you can estimate how many male and female. Okay. Okay, 6.3.4. Okay, how many more? 6.3. Quickly go over, and then we can finish. 6.3. Okay, 6.3.4. 3 permutation. I just want you to apply the formula and then play around with the formula. 6.3.14. What is it? In how many ways can a set of 2 positive integers less than 100 be chosen? So you got 99 of them, and then you want to pick 2. Order is not important because it's a set. It's a set of 2 positive integers. So set doesn't care about order. So I just use combination. Don't use permutation. 6.3.28. What is it? 13 people on the football team show up for the game. How many ways are there to choose 10 players? Yeah, this one just choose. So choose. How many ways are there to assign 10 position? Okay, you see, position. Position meaning order is important. Okay, who is the first one, second one? Who have to play this? Who have to play the different positions? Who have to shoot? Who have to defend? So P. So use P. So order is important. Use P. C. Of 13 who show up, 3 are women. How many ways are there to choose 10 players to take a few? At least one of these must be women. So you can use the previous calculation and then minus 1. Why? Because why? Choose 10 players to play at least one of the players. Because there's only one way to choose all men, right? So yeah. Because out of 13 choose 10, there's only one choice is all men. Next. Okay, this one. 6.4.2. 6.4.2. Okay, find the expansion of this binomial. Yeah. So there are 2 ways to find. One is combinatorial way. One is binomial theorem. So one way is you explain how you get this by expanding this. I mean, you don't expand it. You can expand it to experience yourself. Okay. You can try to expand, do the most primitive way, and then try to experience how to find the coefficient of this guy. Okay. And then the next one is you use the formula to find and then see them match up together. and then 6.4.8. Okay, yeah. So 6.4.8. Then this one, if you want to expand something like this, then if you do it the original way, then it will be headache. You have to go until 17. Right. So if you know the formula, you just keep track of the coefficient of this guy, okay, in front of x and y, and then you use the binomial coefficient. Okay, this is the last one. Yeah, this is the last one. Okay. Okay, thank you. See you next week.
我不太懂这一题，就是这一题题目是说，就是有6个教授，然后呢，就是有一个学生，至少有2个学生跟他的同一个教授取得了相同的分数。那为什么是6乘101，不是101的6次方呢？为什么是6乘101，不是101的6次方？就是大家。就是这个有6个教授，他就是这样C101分之1。
所以他一位教授有
101个可能，对，6个教授或者是不是101的6次方？
那太多了。
就是你有101可能，我有101可能，我们2个的合起来的情况相乘。为什么是6乘101？不太理解。
是，但是你要让它就是出现有重复的情况，你就是只要比它每一种情况它都发生过的再多一次。
他的问题不是这样，他的问题是 OK， 我们不要101了，我们放2就好。2啊，我们放2。A 的可能性有1、2 ，B 的可能性有1、2。OK，你的可能性已经包含了1、1、2。你都不用pigeonhole，他们已经遇到了。是吗？
这什么意思？
就是
2个学生有分数。
对，就是你已经数太多了。因为你是数完所有的可能性。
对。
所以意思说，连这个相遇的可能性都被你数进去了。明白吗？可以明白吗？我现在数的只是说有几个 destroy 的。
就是你这6乘101是保证他们
你只需要有一种情况保证它就可以了，因为他只求的是有多少学生能让两个学生和他相同，我们只需要搞一种，就和他们都是。
我数的是那个 pigeon 的那个 hole， 就是有多少个不同的会有不同的可能性，但是你是数所有的可能性，
不是所有可能性，那这有什么区别呢？
但是你如果数完所有的可能性，当然
会有很多重复的可能。
对，就你对。
我们要保证的是只有一种重复的可能性。
也没有说要保证，就是说我们就
每一种可能都发生过一次，就是它还要再发生一次，
就
一定会有重复的，
就可以。对。
那我回家再理解一下。
就是对，看看这个题目，题目怎么问的？题目说最少他要叫你找最少的那个。
对，他说多少个学生可以保证那个有2个学生跟他的相同的教授，然后他们有相同的分数。
OK， 其实这个题目更好一点，就是说。就是说，至少他要至少多少个学生才能保证他会这个？如果他只是说多少就可以保证的话，这样你的数可能也可以保证，因为你的数已经大过那个
好几倍
对。
那2个学生如果改成1个学生，就是至少有一个学生跟他教授有相同的分数。
一个怎么
有相同？
一个怎么比？2个才可以比。
那如果3个人？
那3个人的话
就比较复杂，
比较大。
对。
那就是应该是606乘以2+1。
这我
要想一下。
我去想一下。
你想一下。
好。但结果不会再。
可以。
现在可以看上次考试的答案吗？
不可以啊，因为有学生还没考。
我不会说的。
你不会说。
那你的审计是
就是
他要做
结束
replacement
才出完了才推，就是他成绩是会最近出还是整个 sem 结束才出来？
就是他是学生全部考完了，然后就出，
还是就是
等最后
好像
最后
那个出那个 coursework，是 coursework 嘛？对，就是 coursework。
成绩啊，我只会给你们看一下有没有修改，像quiz项目没有修改就没有修改哦，有修改我就会改一下，就这样吧。Yeah，因为你们的成绩的话，也不是说你这次考多少，你的 final 一定是多少，就是他会调
这里这东西什么？你跟太差就不能继续翻了。
哦，那个是真的，那个是如果你太
哇哦，
没有，那个是那个 double pass through， 那个 double pass through 意思说你们50-50嘛，50 final 50 midterm 跟 quiz 嘛，你只要保证这个50里面你是20以上就可以了。
什么意思？你要会加你这一段20%才能继续翻的意思。
不是继续 final， 就是你 fail 有没有 fail 这个 course 的意思。继续 final 可以去考试是80%的 attendance。
他们是讲，
谁？讲吗？
他们讲，如果你要 midterm fail 你就可以直接不用来，因为你都要 retake 啊。
我想一下，你 midterm fail 是什么意思？你 midterm fail 的话，你是少于40哈。
就是 fail
midterm 的意思是什么 ？midterm 里面有
不一定不是。
你看啊，你 fail midterm 的意思是什么？你的 midterm 是5/3嘛？如果你 midterm 的 fail 的话，你会拿到40%，3/5的40%是吧？啊，15罢了。OK， 15啊，你看15，你拿到15或以下，那你的 quiz 只要保证5%以上就可以了。
8%是什么？
搞个一个
quiz 的5%是什么？
我不知道。
5%？
5%，20的5%是多少
是几个线而已。
？20的5%。1%，
12.5。12.5。
不是。
5%是12.5，
一分吧。
是1分吗？有没有算错啊？对，但是是不是这样乘？我有没有乘错？没有啦，不可能，不可能。
那个什么东西啊？
反正就是你那个东西，你要20%就可以了。
因为是50%的50% 里面的40%， 50% 里面的40%就是20%，对不对？所以你的 quiz 加你的 midterm， 当50%嘛，对不对？总分50分啊，这样子想啊，里面你要拿到20分，然后你再去想一下，如果你的30% fail 的意思是什么？然后你要想一下你的 quiz 要拿多少高才不会 fail， 可以明白？
明白。
可以啊。OK， 去算一下。
那个 combination application 啊，这个可以按。
可以了。
就那个 step。
可以。
可以啊，就你这样子直接写一个等于多少，你可以吗？
你讲后面这个哈。
他就可以写最后一行。
呀。就算如果没有 calculator 啊，我也可以接受这个。
就直接等于这个吧。
呀，这样复杂的东西不重要啊。这样重要，这样就不要乘出来啊。我们不在意乘出来什么答案，我们在意知道怎么算吧。
OK。在意乘出来什么答案？在意乘出来过程的步骤呢？
那如果乘出来错，只是计算机按错吧
？OK，可以就是
看了，
还是要写步骤，还是要写 step 吗？
当然了，你不可以这边全部丢掉，你只写这个给我，没有分的跟你讲啊，不可能啊。
还是不能 calculator 按。
你不可以 calculator 按这个东西，你可以 calculator 按这个东西。
我能不能只写这一步，然后出来这个？
对，我就想问这样。
中间
就整个边
东西啊。
可以直接按了。
我们可以就这个可以，但是按得错吗？
对。
其实这个东西留下来都已经是个答案了。
这个对，但是他如果可以约减的话，就是最好的答案嘛。对不对？能够约的。
如果我写成，我不要写这个，要约的我就直接抄成个这样子，然后我再等你这个可以。
计算机算不了这么多位。
可以了。
但是一定要几个？
但是这个比较美吗？这个。
美太难了。
可以了。但是你至少要有这些东西。
OK。
老师，请问这样出去。
那位同学不要问他，你要问吗？
对，请病假有占出勤率吗？
请病假有什么？
有占出勤率，
什么意思？
就是请病假算缺勤。
没有啊，
哦，
病假可是你要跟那个 OAA 申请啊。
病假算缺
对
勤
对对对对，
这也知道
那
个
东西。
就是
对，你要呀，对对对
他跟我提交我
对对对对对，你要那个，你要跟他透过他。
这个它为什么是2台？
怎么说？
我不知道。
你说为什么要剪掉啊？啊，再讲。
你想问什么？
问我再问。
错啊，不是 and，它是
两个情况。
它是00或者333，不是00。
啊，对对对对，他意思是哦，所以意思说你00后面没有3也行，或者前面没有00后面有33就行。呀，哦呀。
那它 string 的话，它的开头可以是0，
可以是0，因为它只是字符串。
没有，它是 bit string，bit 的话是0跟1嘛。
啊，他是说前面有一个那个
哦，可以
4位数的那个。
啊，4位数的那个。
就是前面有一个那个4位数那个题，我前面有一个1位数是0，然后一直在运行。然后想这个那个后面减的那一个要怎么算？
减的那个要怎么算？
对，
减的那个是因为你在算所有的可能性的时候，你同时也把这个111的可能性算进去嘛，对不对？相等下面也是哦。
然后他也把就是那个11的那个把00的给带进去了。
对对对对。
所以这个是重复的
啊，这个重复。
去掉的话，那就是2乘以2的平方。
因为你要去掉所有这个的可能性。
对。
所以这个中间呀。
然后
2乘2种，
它有两种，就是要么00或者要111的，所以它还要4还要再乘2就减8，这样吗？是减8，我有点忘记。
减4，对。
但是
2个洞嘛。
但是它这个是4种。
对，然后呢？
你上面不是计算过了一次？就比如说上面已经计算过0.0.100.00111这4种。上面计算过一次，下面不是还会再计算一次吗？那这4种不是应该再乘2吗？
减1次就好了。
要保
留一次。对，不然你没有算到。对。啊对。
哦 ，OK，
减1次就行。
那个哥曹定理可以直接写直接用吗？
可以。
就是直接说根据哥曹定理，所以这个一定是成立的。
就是你要说它有几个曹几个哥，你只要保证那个哥比曹多至少。
就只要写这一句话就可以。谢谢老师。
OK。